Hello everyone, welcome to my channel, The Teaching Show. Please like, subscribe and press the bell icon for more updates. So in this series we are seeing problems on thermodynamics. Again in this video we will take two more problems. First problem in this video deals with again a reversible refrigerator. I have taken one problem on reverse Carnot cycle or refrigeration cycle in my first video. If you have not seen that video, you can go and check that. So let's start with this problem. Okay, so the problem statement here goes like this, that the internal energy of a certain quantity of a particular ideal gas is given by U equal to Ct. Okay, so as the temperature is changing, the internal energy is changing. So I can also write it in a differential form as du is equal to C dt. C is a constant and given as 10 joules per Kelvin. Okay, remember that temperature which we use in thermodynamics is always Kelvin. Okay, now so what is happening basically is that this gas, it is being cooled from 290 Kelvin to 0.5 Kelvin. In order to cool this gas, some amount of heat is being extracted from this gas, which is given as Qc dot. Okay, so Qc dot is basically the rate at which the heat is extracted from this gas. Okay, using a reversible refrigerator, in order to extract this gas, what we have to do? We have to do a certain amount of work. So the rate at which the work is done is given by W dot. And then it is now rejecting heat which it is extracting from this gas. It is now rejecting this heat at a high temperature thermal reservoir at 300 Kelvin. Okay, so let's see how to tackle this problem. Okay, so since the gas is being cooled, first of all we have to find out what is Q dot C. So in that case, so the gas is being cooled from 290 to 0.5. So the rate at which this heat is extracted, Q dot C, that should be equal to the change in the internal energy of this gas. Okay, so I'm just first of all I'm focusing on this gas and writing first law for this gas. So since if I take my system as this gas, then no work is being done, then the change in the internal energy of this gas should be equal to the heat which it gives off. Okay, so the energy balance for the gas cooling at constant volume is given by du by dt is equal to minus Q dot C, because the heat is getting out of the system, so I'm taking it as negative. So there is a change in internal energy which is given by minus Q dot C. Now we also know that the coefficient of performance for a refrigerator cycle is given by 1 upon Th by T minus 1. Okay, and that is equal to Q dot C upon W dot. So here note one thing, that T is changing with time. That's why I am using all this equation in a rate form. That is, the Q is the rate at which heat is extracted, and W is the work, the rate at which the work is being done. Okay, because here T is changing in this equation. Okay, so now what I'm doing is I'm rearranging this equation in terms of W dot. W dot is nothing but dW by dt, that is equal to 1 minus Th by T into Q dot C. Okay, now Q dot C is minus du by dt. So I am writing, instead of Q dot C, I am writing du by dt, and the negative sign is absorbed in this bracket. Okay. Now again from the problem statement we know that U is equal to Ct, or I told you that du is equal to C dt. So I am going to put du by dt as C dt by dt. So the dt thing, it gets cancelled, and what I am left with is dw, that is the change in the work or the differential amount of work which is done, that is equal to 1 minus Th by T C into dt. Now the problem is simple now. We have this relation, we have to find out what is the work which is being done. So just integrate this equation from initial state to final state. What is the initial state? Initial state is when the temperature T1 of the gas is 290 Kelvin, and the final state of the gas is 0.5 Kelvin. So we have to integrate from temperature T1 is equal to 290 Kelvin to T2 is equal to 0.5 Kelvin. Just put these values and integrate it between these limits. Also we know that TH is fixed at 300 Kelvin. So integrate this, put all these values, and you get what is the amount of work which is required for cooling this gas is 16,194 joules. Okay, so this problem is very simple. It just requires some mathematical manipulation. Otherwise, it's a very straightforward problem. Okay, let's look at problem number 6. Now, problem number 6 is a piston cylinder type of problem. Again, this is a closed system. Okay, and let's first understand this problem. So, what is happening? This is the cylinder, and this shaded thing is the piston. Okay, now piston is resting on two stops, and if the pressure rises, then this piston can go up. Okay, but it can go up only to a certain extent, where then it again hits two more stops. Okay, so initially the water is present inside this cylinder. The volume which is occupied by this water is 0.4 meter cube, and the pressure is 100 kilopascals. Now it is given that the quality of steam is 0.2, that is, it contains 20% vapor and 80% liquid water. Okay, now at an instant, heat is being applied. So I am applying Q. What happens is that now as the water is heated, its pressure starts increasing. So it increases, let's say up to a point, say 300 kilopascal. This is the pressure which is required to move the piston. Okay, so piston will not move unless and until the pressure applied to that piston is 300 kilopascals. So the pressure keeps on increasing and the piston doesn't move, but it starts moving as soon as the pressure inside the cylinder reaches 300 kilopascals. So this is what is happening now over here. This piston, it moves up and then it again hits these stops. Okay, so the point when you are supplying heat and the piston is at rest, then this is a constant volume process. Then after that, what is happening? When the pressure is increased to 300 kilopascal, then this is a constant pressure process till your piston reaches the upper stops, and then after that again the pressure starts rising. Okay, so let's apply the energy balance for closed system. Energy balance for closed system says the change in internal energy, that is equal to heat exchanged plus work which is done. Okay, or work. So in this case, we have been asked to find out what is the amount of work which is done, what is the heat which is supplied, and also the final pressure inside the cylinder. Okay, so in this energy balance, let's see what quantities we know or we can calculate. M we don't know, but we can calculate. U2 and U1, that is the internal energy at the final and the initial states. Again, we can find out using steam tables. Q we have to calculate, W we have to calculate. So let's tackle this problem. So first of all, we will find out what is the mass of the water inside this cylinder. Okay, so let's see. What I can do is I can use steam tables to find out this. I know that initially the pressure is 100 kilopascal and the quality of steam is 0.2. So I will just see a saturated steam table. Okay, 100 kilopascal is 0.1 megapascal. So I will read what are the values of the specific volume for gas and for liquid. I have read these two values, that is Vg and Vf. Then I calculate what will be the specific volume of the wet steam with a quality of 0.2. So I find out the volume, the specific volume of steam, which is 0.3396 meter cube per kg. The total volume given is 0.4. So if I divide the total volume by the specific volume, I will get the mass of steam inside the cylinder. So mass of the steam is 1.178 kg. Now I have to again find out what is U1. U1 also I can read from the steam tables. Here I am seeing that Ug and Uf. UG is 2505.5 and UF is 417.4. So I'm using these values along with the quality of steam to calculate the internal energy at the initial state. Now let's move and calculate what will be the internal energy at the final state. Okay, so at final state, how do we find final state? What is given? What information is given? That water is a saturated vapor. Okay, and the volume is 0.6 meter cube. So the total volume is 0.6 meter cube. We know what is the mass of the steam. We have already calculated. It is 1.178 kg. So now we can calculate what will be the specific volume at the final state, which comes out to be 0.6 divided by 1.178. So it is 0.5093 meter cube per kg. If we just go in the steam table and read the specific volume for 300 kilopascals, okay, what we find is that this volume, the specific volume, is less than the specific volume of the saturated vapor at 300 kilopascal. What this suggests? This suggests that the pressure inside is higher than 300 kilopascal. Okay, so in order to find out what is the final pressure, we will again go to a saturated steam table and try to find out where this value lies. Okay, so I'm just scanning the steam table and I'm looking for a value of 0.5093 till I come across, you see, I will start from 300 kilopascal. So this is 0.3 megapascal and I will keep on looking in the steam table till I hit this value. Okay, this is 0.5105. In the next value is 0.49. Our value lies in between these two. That is, one value corresponds to 360 kilopascal, the other is 370 kilopascal. So we have to interpolate between these two values. Okay, do a linear interpolation and find out the pressure value which corresponds to a specific volume of 0.5093. So that's what we had done. I have calculated the pressure value as 361.3 kilopascals. You can also go and do the interpolation yourself and confirm with my result. Then again, I know I have to calculate now U2, that is the internal energy at the final state. That should be equal to the internal energy of the saturated vapor. So what I will do is I will again go and interpolate between these two values, that is 2549.4 and 2550.4. So I will interpolate between these two and I get the value as 2549.6 kilojoules per kg. Okay, so now I have mass, I have U1, U2. The only thing which is left, which needs to be calculated, is the work done. Work done is basically given as, this is PV work, so it is equal to P into V2 minus V1. Work is being done only when the piston moves from between these two stops. Okay, and when the piston moves, the pressure remains constant. So the external pressure remains constant at 300 kilopascal and the volume changes 0.6 minus 0.4, that is 0.2 meter cube. So the work done is calculated simply as P external into V2 minus V1, that is 300 into 0.2. That comes out to be 60 kilojoules. Okay, so this is my work done. Now I will just plug all the values which we have calculated. M as 1.178, U2 is 2549.6, U1 we had seen it was 835.02, that is equal to Q minus 60. So I am now calculating what is the heat which needs to be transferred in order to carry out this process. Okay, so this video ends over here, and I hope this was informative to you. So thanks for watching, and please like and subscribe to my channel, and also see the other videos which I have uploaded before on problems on thermodynamics. Thanks a lot for watching.